All right, so that was Good Vibrations by the Beach Boys to get us geared up for a lecture all about vibrations. So this will start a little bit unconventionally. So I'll start with a map of Europe, and then hopefully it will become clear how this connects to vibrations by the end. So this is a map of Europe in 1812. And so 1812 was around the time that Napoleon had control of most of Europe. And so everything outlined in red here is territory that was ruled by Napoleon's empire. And so as any kind of emperor or authoritarian back in the 1800s, this wasn't enough. So he wanted to conquer the whole world. And so he went after this large territory to the east of his current territory called Russia. So this turned out to not be such a good idea. So what I'm showing here on this map is, in red is the number of troops in Napoleon's army. And on the left is before he invaded Russia. And then this is kind of the dwindling number of troops, or the dwindling red bar as he approached Moscow. And then the black bar is then on his return trip from Moscow to France. So this amounted to...
Can anyone else only see like a small strip of the screen, like nothing east of Germany?
Oh, really?
I don't know. Maybe it's just me.
It's me too.
Cool. Thank you.
All right. Thanks. Let's see.
Better. Thank you.
Cool. All right. So here's the map of Europe. So this is all of Napoleon's territory. And then here in this top figure is his loss of troops moving from left to right as he approached Moscow. And then eventually when he returns back to France, he just has this small black dot left. So he lost about 90% of the men that he traveled with. So urban legend would have it that the French army back then was equipped with uniforms having tin buttons. And tin has this interesting property where the form of tin we're mostly familiar with, the one that exists at room temperature, is this whitish or silverish beta tin shown on the right. But if you get to cold enough temperatures, so thermodynamically at about 13 C or below, it should transform into alpha tin, although in practice this occurs at much lower temperatures, about minus 15 C. And so once tin transforms from beta tin to alpha tin, it loses kind of its more metallic properties. So it becomes extremely brittle and almost like chalky. So it basically disintegrates. And so urban legend would have it that as Napoleon's army approached Russia and then started fighting in Russia, their uniforms eventually fell apart because their buttons could no longer hold up their clothes. And so presumably this was a result of tin disease or tin pest, where beta tin transitioned to alpha tin during the cold Russian winter. And by the end of this lecture, you'll see that this transition from beta tin to alpha tin and the destruction of Napoleon's empire was actually a result of vibrations in the solid state. All right, so let me transition here. All right, if I turn my iPad vertically here, can you still see the screen, or is it cut off?
Look good.
All right, cool, thanks. All right, to briefly recap what we talked about last time in terms of vibrations of a diatomic gas. So I showed a plot that looks like this, where I have the energy as a function of position, where I can draw my two diatomic gas molecules kind of along this positional axis. We imagine them as harmonic oscillators or connected by a harmonic oscillator. So I draw some spring or chemical bond between them. And then I can draw some potential energy, where the lowest energy is at this equilibrium position, so the position I've drawn them at. And then we have these various energy levels where, as this spring kind of vibrates or these atoms move in the vibrational direction along the spring, we have a change in energy. And so this is a diatomic gas as a quantum harmonic oscillator. And we know that the energy levels for the system are discrete or quantized. So the energy of some vibrational energy level n is equal to n plus 1/2 times h times the vibrational frequency. And then that vibrational frequency depends on the nature of the system by this relation. So the vibrational frequency equals 1/2 pi times the square root of the spring constant, which is kind of like the bond stiffness, and then the reduced mass, which accounts for the masses of the two atoms attached to the spring. And so what this says is that frequencies will increase as the stiffness of bonds increases or the mass of atoms attached to the spring decrease. So then we can write our vibrational partition function, which we derived last class. It's just e to the minus beta h nu over 2 over 1 minus e to the minus beta h nu. So we talked a bit about this quantity beta h nu last time. So we can define the vibrational temperature. Theta sub v just equals h nu over kb, where kb is Boltzmann's constant. So this just allows us to think about the scale of vibrational frequencies on the same axis as temperature, or as on the same axis as the thermal scale. And so we can rewrite our partition function in terms of this theta. So that's just e minus theta b over 2t, 1 minus e to the minus theta b over t. And then, per usual, we go from this statistical mechanical space of partition functions to our thermodynamic space using partial derivatives of the log of the partition function. So the vibrational energy is just nkt squared times the partial derivative of log of q with respect to temperature. And then the main topic of today's lecture will be on the specific heat or heat capacity. So the vibrational contribution to the specific heat is just the partial derivative of the energy of vibrations with respect to temperature, with all else held constant. And if we're at high T, which might be defined as T much larger than the vibrational temperature, then we know for a diatomic gas, the heat capacity approaches Nk, where this Nk arises because of the equipartition theorem. So we have 2 vibrational degrees of freedom, and so we get 2 times 1/2 kT contributions to the energy, and so a single Nk contribution to the specific heat. All right, does anyone have any questions on the diatomic gas before we move on to a similar workup for solids? Cool. Today would be how to think of the key odds. So vibrations in each direction, x, y, and z, and then 2 degrees of freedom per vibration. And so that means that the specific heat at high temperature should go to 3 NK. So this is if we're thinking in terms of the equipartition theorem, but actually about 40 years before the equipartition theorem was developed, two guys, Dulong and Petit, noticed from experimental data that this law should actually hold. So he basically said, or they basically said, the specific heat goes to 3 NK at sufficiently high temperature, no matter the makeup of the material of interest. And so this actually works pretty well, assuming you go to high enough temperature, but it doesn't tell us anything about the behavior of CV at low temperatures, at room temperatures, or any kind of material specificity for why a certain material's heat capacity should go faster or slower to 3 NK. And so about 80 years later, so now this is well after the equipartition theorem was developed and kind of the dawn of quantum mechanics starting to emerge. A familiar guy, Albert Einstein, developed a model for how vibrations work in solids. This is 1907. So Einstein made a couple of assumptions. So he assumed one, that a solid is comprised of 3n independent harmonic oscillators, quantum harmonic oscillators. And then the second major assumption is that all of these oscillators vibrate at the same frequency. We call that nu sub e, or the Einstein frequency. So then this means that for all 3n oscillators in the system, we have nu1 equals nu2 equals nu-n, all equal to Einstein's frequency. So then the energy of any energy level is just n plus 1/2 times h times Einstein's frequency. And so we get almost an identical form of the partition function as for the diatomic gas. So the vibrational partition function, sum over all states of e to the minus beta times the energy levels. And so this has the same form I wrote above, except now we're substituting an arbitrary frequency nu for specifically Einstein's frequency. And similarly, we can define a vibrational temperature specifically for Einstein's model, the Einstein temperature, which is equal to h nu Einstein over kb. So in his model, he's basically stating that within a given material, all of the atoms should be vibrating at the same frequency, but the actual frequency depends on the nature of the material. So a stiffer material would have higher frequencies than a soft material. And so that would be roughly captured by Einstein's temperature. So Einstein's temperature would say we have higher Einstein's temperature as bonds get stiffer, or atoms get lighter. So then following essentially the same derivation as for the diatomic gas, except now we have 3n molecular partition functions instead of just n. So our overall system partition function would then be related to Q raised to the 3n power. So this would be Q vibe. And so just as before, we can say that what's the average energy of the system? And it's going to look very similar to what we derived before. Where the main difference between this expression and the one for the ideal gas is just this 3. And similarly for the specific heat. And so once again, this is identical to as before, except multiplied by 3 because now we have vibrations along 3 dimensions. So this model is good in terms of high temperature. So for T much larger than Einstein's temperature, we do get the behavior that we'd like. So we follow Dulong-Petit's law that the heat capacity goes to 3 nkb. So if we recall that Einstein's temperature is proportional to the frequencies, if we were to draw a plot of the specific heat as a function of some normalized temperature, so T over the Einstein temperature, then we would get, for any material in theory, we would get a curve that kind of looks like this. So once we're above Einstein's temperature, then we get to the 3 nkb limit. And so this is plotting CV as a function of this normalized temperature. So in reality, each material of interest will have a different Einstein's temperature. And so if we plot this same curve, but now as a function of the absolute temperature T, we still have this 3 nkb limit. But the way materials approach that limit will be different. So I might have one material that gets there rather quickly, a second material that takes a bit longer to get to the limit, and so forth. And so as I move from the lighter color to the darker color, can anyone guess which of these has the largest Einstein's temperature? So thinking again that Einstein's temperature is going to be linearly related to the magnitude of these vibrational frequencies. So should a material with high vibrational frequencies get to the 3 nkb limit sooner or later as a function of temperature? Any ideas?
Sooner?
So a material with higher vibrational frequencies actually gets there later. So I'm increasing the Einstein's temperature as I move down from light to green. And so we can think about why that is. So Einstein's temperature is proportional to these frequencies. And then we know the energy is going to be proportional to these frequencies. And so if I have very large frequencies, that means my energies are very much separated. And so it takes higher and higher temperature to populate larger values of n. So we could say that as nu E increases, kind of En plus 1 minus En also increases. And again, this new E is just going to be proportional to the stiffness of the bonds divided by the reduced mass, square root of that. So you can think about it like the sooner I'm getting to the high temperature limit for the heat capacity is the sooner I've consumed all of my vibrational degrees of freedom. So the sooner I'm kind of accessing larger and larger values of N. So that's why a softer material gets to this high temperature limit quicker. So we can also think not only about the heat capacity, but also about the entropy. So I'll draw two different situations. So here we have some potential energy as a function of position. And then I'll draw another one, try to make these roughly similar looking. So let's say I have one potential energy surface that kind of looks broad like this, and then another one that is much more narrow. Then I'll draw what these energy levels look like as a function of N. So this might be N equals 0, N equals 2, and so forth. And if I have a tighter potential energy surface, then I'm going to have larger separation of those energy levels. So you can kind of think about this like, here are my atoms on a spring. If I have a very tight spring on the right, then displacing one of those atoms or moving that spring is going to come with a very large energy penalty as this atom kind of moves away from its equilibrium position. And so that would be characteristic of high frequency vibrations. So we know the energy is proportional to these frequencies. We know the entropy is KB times log of the number of states. So do we have a guess as to whether the entropy is larger or smaller for a tighter spring?
Is it larger for tighter or for a less tight spring?
Yeah, exactly right. And why do you think that is?
There's more energy states.
Yeah, at a given temperature, we're able to explore more energy states. So this would be kind of a low Einstein temperature, high Einstein temperature. And so if we have smaller frequencies, so that means lower Einstein temperature, we can explore more microstates at a given T. So if we're decreasing the frequencies, that means we're decreasing the spacing of energy levels. That means we're increasing the entropy. And you can also get to the similar result thinking about how the entropy and specific heat are related. So we know kind of from what I showed above that if we have a softer material, we're getting to a higher specific temperature.
Question about the
Sure.
graphs. So if I wanted to imagine the temperature graphically on each of these energy versus R plots, could I just draw a horizontal line and that represent like everything below that are the energy states I could access?
Yeah, you could definitely kind of think about it that way. So as I go to higher temperature, I'll certainly be populating higher values of N. So you might think at very low temperature, I'm only maybe filling up to here. But if I go to higher and higher temperature, then I'm exploring more of these configurations that are off of the equilibrium position. Does that answer your question?
Yeah, thank you.
Cool. All right, so let's think back to CV. So we're trying to find a model for the specific heat of solids, or for vibrational modes in solids that recreates experimental measurements of specific heat for a range of materials. So for Einstein's model, we know it gets the high T behavior, where that's just CV approaches 3 NK. At low T, CV is supposed to go to 0, and Einstein's model reproduces that. But kind of somewhere in between the high T and the low T, it goes awry. So it's known experimentally that the heat capacity should go with T cubed as you get to low temperature. So as you approach 0, it should have a cubic dependence on temperature. But unfortunately, Einstein's model does not do that. So at low T for Einstein, he would say that CV goes to 3 NKB times Einstein's temperature over the absolute temperature squared times e to the minus theta over T. And so unfortunately, this does not equal T cubed. So he almost got it, but not quite. So then about 5 years later, Debye came along and tried to come up with his own model that would still meet these high and low T limits. So at high T approaching 3 NK, at low T approaching 0. But he really wanted to see how could he model the system such that you recreate this cubic dependence of the temperature. All right, so I'll start by just rewriting what is the vibrational partition function. And I'm relaxing Einstein's assumption that all of these frequencies are the same. So now I'm just writing this general nu here. So then the overall partition function could be written as a product over all of these states, I. If we assume these are continuous, so that means kind of spaced closely together, then we can convert this product into a sum by also taking the log. Or sorry, we can convert the product to a sum by taking a log, and then convert that sum into an integral by assuming continuous spacing. So now, just like in previous situations where we've shifted from summing over states to summing over levels, now we're going to shift from summing over states I to summing over each of these frequencies nu. And so if you remember, when we switch from summing over states to summing over energy levels, then we have to account for the degeneracy or the density of states. And so that will be accounted for by this arbitrary function G. So this is more or less an exact expression, the one I've shown here, except we don't a priori know what this function G looks like. So that'll be the goal of this next kind of workup. What is the density of states in frequency space? So if we recall Einstein's model a bit, another way to think about his model. So he assumed that, you know, every frequency was equal to a single frequency, the Einstein frequency, within a given material. So he's essentially saying that the density of states is related to a delta function, where if the frequency is equal to Einstein's frequency, that turns on that mode, and if it's not, then it turns off. But again, we know that Einstein's model doesn't recreate this T cubed behavior at low temperature, and so we need to do something else. So Debye thought about, first off, relaxing this approximation or assumption that all of the frequencies within a material are the same. And instead, Debye imagined that the behavior of vibrational frequencies within a solid, a periodic crystalline solid, would be similar to the behavior of light within a black body. So that really means he's modeling these solid vibrations as waves. So waves in a periodic material, that means we have standing waves. All right, so to try to understand Debye's model, we're going to take a quick departure from thermodynamics and now think more about solid state physics. So this will be kind of an intro to solid state physics if you haven't had one, but condensed to maybe 15 minutes or so. So imagine we have a 1D chain of particles in a periodic potential. So I'll try to roughly draw what that might look like. So these circles are my particles. I have some potential energy in the space. I'll draw in pink. So that potential energy is periodic. So it looks the same around each particle, even though my drawing doesn't quite look the same. But you can imagine we have some kind of repeating unit along this 1D chain. So then we can invoke what's called Bloch's theorem for waves, standing waves in a periodic system. So he states that you can write the wave function for that standing wave is equal to e to the I kx times u of x. And so you'll find that it's going to become convenient for us to think in terms of this value k. So this is called the wave vector, or the reciprocal lattice vector, or reciprocal space vector, or sometimes the momentum space vector. And it's really just a way for us to handle a periodic system. So it's not so easy to work up the math of periodic systems in real space. And so instead we operate in reciprocal space. So this is just the general function for a plane wave or a standing wave. And then this function u is just some periodic function. So we know we're in a periodic potential, which means that we have some periodic function where the value of that function at x is the same as the value of that function after some periodic separation. All right, so in a periodic space, it's sometimes easier to think about a monoatomic chain of particles, where here I'm at x equals 0, here I'm at x equals L, can actually be represented as a circular ring. So here are those same 5 particles, but now because we're in a periodic space, we know all functions of that space should be the same at the spacing of that periodicity. So I can say that I have a single point that represents x equals 0 and x equals L. So I have the same behavior at these 2 points. So kind of plugging in Bloch's theorem, I can say that the wave function at 0 should equal the wave function at L because of the periodicity. And I know that this arbitrary function u is also the same at 0 and at L. So that allows me to write that the wave function at 0, plugging in for x equals 0 equals e to the I k times 0 times u of 0. And because that equals the wave function at L, that also equals e to the I k L times u of L. And then u of L is also equal to u of 0. So that's e to the I k L times u of 0. And so what that says is that e to the I k 0 must equal e to the I k L. And then that means e to the 0 equals 1. So that's 1 equals e to the I k L. And if we invoke Euler's identity, we can change the exponential into a cosine plus I sine of what's in the exponential. And then we have periodic solutions to this expression. So that means our allowed values of k are related to 2 pi over L times n, where n can go from 0, 1, 2, etc. So what this tells us is that this wave vector k is quantized. So this is for a 1D chain, but we can apply the same workup in 3D. So for a 3D solid, I now have some vector k, but I have the same spacing except in all 3 directions. So why am I doing all of this? Remember that my goal is to come up with the density of states in frequency space. So that'd be G of nu. So to get there, it's handy to know what's the density of states in K space. So I start again with this expression that I wrote just above. Where our periodic boundary conditions dictate that this constraint is met. Then some simple manipulations, I can say this n over k equals the volume of our system divided by 8 pi cubed. And so what does this n over k mean? It's a bit abstract. So it's really just saying that these are the number of allowed values of our wave vector per unit volume in our momentum space or reciprocal space. So if I wanted to say what are or how many states do I have? Are present for a given value of k. So kind of within some constant k space. I would say this function, the number of states phi of k is going to be equal to the number of states in a given unit volume. times the volume in K space given the K I'm interested in. So for instance, I said K equals pi. I want to know how many states are contained in that volume that's formed by K equals pi. So again, this is just the number per unit volume. And this would be the volume at the K of interest. So this simplifies to phi of K equals the volume over 6 pi squared times K cubed. So I know phi is the number of states. So if phi is the number of states, I can say that d phi equals the density of states times the increment. So basically this comes from knowing that if I integrated the density of states from 0 to infinity, so over all frequencies, then I would return all of my possible states. So if I know this is true, d phi equals g of v or g of nu d nu, then I just rearrange and I can say g of nu is equal to d of phi d nu. So the density of states is the differential of the number of states with respect to the increment in the variable we're interested in, which in this case is nu, the frequencies. So far I only know what is phi of K, but I really want to be in this frequency space instead of wave vector space. So I can perform a simple variable exchange. So g of nu is then equal to d of phi dk times dk d nu. And I don't know yet what this dk d nu looks like. But at least now I'm getting closer to figuring out what is this density of states. All right, so we also know from Planck's theory of black body radiation that there's a dispersion relation that relates the angular frequency of waves to the velocity of those waves times the wave vector k. So again, this is our angular frequency omega. This is the velocity of the wave, so the speed of light in the case of black body radiation, and the speed of sound in the case of vibrational waves. And this is our wave vector k. So in our previous workup, what we're really looking for is the density of states in nu space. So nu is the normal vibrational frequency, which is just related to the angular frequency by 2 pi. All right, so my goal is to get what is g of phi equals d phi d nu. So this is d phi dk times the dispersion relation in omega space, and then converting from omega space back to our normal frequency space nu. And if I remember that phi of k equals v over 6 pi squared times k cubed. So now coupling this along with our dispersion relation, now we know what all of these values should be. So I can write that g of nu just plugging in now. So the derivative of phi with respect to k is going to be is that right? Yeah. Times k squared. And then the derivative of k with respect to omega is just 1 over c. And then the derivative of omega with respect to nu is 2 pi. So now I'm still not quite all the way there because it's kind of awkward in statistical mechanical space for me to have this density of states in terms of k. So I really just want this in terms of nu. So I know that omega equals c times k, omega equals 2 pi nu, and so then I can rearrange for k in terms of omega. So if I remove that k in favor of omega, I'll eventually get that my density of states in normal frequency space is related to the frequencies squared. So then that looks something like this. Just a quadratic dependence on the density of states. So this is proportional to nu squared. All right, so beyond this, Debye made an additional assumption. He assumed that instead of saying that if we integrate the density of states from 0 to infinity, we return our 3n, we can actually, instead of saying infinity, we can define some critical frequency at which all of the degrees of freedom are consumed. So he said that instead of this, we can say that if you just integrate from 0 to some critical frequency, this density of states, then you'll return all of the states. It's basically saying that this g of v shuts down, so it just becomes 0 once you're above a certain critical frequency called the Debye frequency. So if we plug in what we know for g of nu, then we can solve for the Debye frequency. And we would get that the Debye frequency has this form. So it's related to the density of the material. And you'll also see that sometimes written in angular frequency space, which would then look like this. And so we really have a piecewise function for g of nu, where it equals this 9n over the Debye frequency cubed. So this is just kind of doing some manipulations to get us in a relatively simple space. So I'm kind of plugging in what is the Debye frequency into this g of nu expression just to get a simpler expression. And then otherwise it equals 0. So if our frequency is above this critical frequency, then we have no population of those states. All right, so why do we do all this? We want a model for CV. So we know that, as I wrote before, we can write the log of Q in terms of the single particle vibrational partition function. Times our function for the density of states. You know, CV equals dE dt, and then E equals minus d log Q d beta. And I'll save the trouble of a lot of messy math. If we let X equal this quantity beta H nu, we once again define a specific temperature, the Debye temperature, which is going to be H times this critical Debye frequency divided by Boltzmann's constant. Then we can rewrite a final expression for CV equals 9 nkb times T over theta d cubed times the integral from 0 to theta d over T of x to the fourth e to the x times e to the x minus 1 squared dx. So this would be the Debye model for the specific heat. All right, I know this might have been a little quick, especially if you haven't taken solid state physics or if it's been a while. Are there any major questions at this point? Not so much on the math, but more on the concepts of how we got here. All right, cool. So you can kind of see already that there's this going to be a T cubed term in the specific heat, which is a good sign. And so if I don't get any objections, I'm going to switch screens back to my PowerPoint. So if we've got all of this written down, object now or forever hold your peace. All right, and then I'll switch back to the PowerPoint and rotate. And then just let me know if you can't see this again. All right, so here I've just copied the same expression for the specific heat that I wrote at the end of the last note. And this expression x to the fourth e to the x over whatever doesn't have an analytical solution. And so I just did some numerical integration in Wolfram alpha. So if I say the temperature is equal exactly to the Debye temperature, so then I'm integrating from 0 to 1. And then in units of n times k, I get that the heat capacity equals 2.85. So this means that I'm approaching this high temperature limit of 3 nk, but I'm not quite there at the Debye temperature. But then if I go to a much higher temperature of T equals 10 times the Debye temperature, then now I am hitting this high temperature limit of CV equals 3 nk. And then if I go to a very low temperature near 0, so the absolute temperature being 1 over 1,000 times the Debye temperature, then my heat capacity does go to 0. So this is all a good sign that the Debye model is recovering a lot of this behavior. So it's a bit trickier to show that at low but non-zero temperatures, the Debye temperature or the heat capacity in this model goes to T cubed. But if you take experimental data for a number of different materials and overlay it on what Debye's models predicts, here I'm plotting the specific heat divided by 3R, where R is just equal to N times K for 1 mole. And then plotting that against the normalized temperature, so the absolute temperature divided by the Debye temperature. And each of these markers is an experimental data point at a given temperature for a different material, aluminum, copper, silver, or lead. And then the blue curve would just be the single curve that you get for Debye's model when you're plotting in this normalized temperature space, temperature divided by the Debye temperature. So what we see that's encouraging is that we get the high temperature behavior, but then we also get the behavior at very low Debye temperatures, low but non-zero. So we recover this kind of T-cube dependence that's captured by these last 4 data points at the bottom. So we can also think about the Debye temperature as a surrogate for stiffness in the material. So remember, the Debye temperature is going to be proportional to this critical Debye frequency. So if we have a very strongly bound material made of light atoms, this might be diamond form of carbon shown at the bottom, then we have this very low specific heat at low temperature because we have a very high Debye temperature, in this case 1850 Kelvin. So that just means that the frequencies are going to be very high. And so it's going to take a very large temperature before we've actually engaged all of these very high frequency vibrational modes. So as we move up this curve, kind of along the red arrow, we see beryllium is not quite as well bound together as diamond carbon, but it's still a very light atom. And we're moving slightly heavier. We go silicon, germanium, and then eventually we have a very heavy, very weakly bound metal like lead, where all of these vibrational frequencies are pretty low. And so we're consuming those even at very low temperatures. And then that's characteristic of its Debye temperature of only about 100 Kelvin. Are there any questions on this, kind of the nature of the specific heat in the Debye model and how Debye temperature relates to the physical parameters of the material? All right, cool. So if you remember, Debye got to his model by kind of thinking that vibrations in a periodic solid should behave similar to electromagnetic radiation. And so we know in electromagnetic radiation, we have these quasi-particles, photons. So these are non-conserved bosons, where one photon just represents one quanta of electromagnetic radiation. So similarly, if we think about vibrational energy in a solid, we have an analogous quasi-particle, which is also a non-conserved boson called a phonon. So a phonon just represents a single quanta of vibrational energy. And then let's see if this works. All right, can you see this website? Does it look good? All right, so this is our favorite 2D material, graphene. Try to zoom in a little bit. And so what I'm plotting on the right-hand side of this plot is the dispersion curve of phonons. So along the x-axis, these points gamma, m, k, and gamma, these are high symmetry points within reciprocal space for this crystalline material. And then along the y-axis, these are the different frequencies of vibrations within the material. So if I look at this low frequency state, so around the gamma point, that looks like this vibration. So it's just kind of this low frequency rippling where none of the atoms are really getting close together. So if I go to a slightly higher frequency, let's see. All right, so I went from about 20 wave numbers now to 400 wave numbers. You can see this rippling is getting a little less wavy, and atoms are kind of moving significantly off their equilibrium positions. So I can go to some very high frequencies. So now I'm at 1600 wave numbers, so these highest possible frequencies of these phonons. And you can see now the carbon atoms in graphene are getting really close together. So this is kind of a physical representation for what are these phonon frequencies, or how we get to a density of states of vibrations. All right, and then I'll switch back to the PowerPoint. And so this function g of nu that I talked about earlier is really the phonon density of states, so the density of vibrational states. So in the Einstein model, remember, he assumed that every single vibration occurred at the exact same frequency. So the density of states is just this vertical line. The Debye model says this density of states should be quadratic, but then stop at a given cutoff frequency. And then if we look at the density of states for a real material like silicon, which would be developed by looking at these different vibrational modes of the lattice in silicon, you can see it kind of has this Debye-like dependence, where you can draw this quadratic relationship very roughly over these frequencies. All right, so let's think again about tin. So remember that tin has a phase transition from beta tin to alpha tin at very cold temperatures. And so here I'm plotting what is the phonon density of states, so the density of states for vibrations for alpha tin, which is the low temperature phase up top, and beta tin, which is the high temperature phase. So if I say that these phases have a phase transition at 13 degrees Celsius, if the system's under constant pressure, then that means that the Helmholtz free energies of these two phases are equivalent at 13 degrees C. And then it's known from quantum chemical calculations that the alpha phase is slightly lower in energy at 0 Kelvin. So the difference in energy between the beta phase and the alpha phase in terms of internal energy is about 2 kilojoules per mole. So given these two facts, does anyone wager a guess about what this says about these two phases' relative entropies? So if I know that the internal energy of the beta phase is higher at 0 Kelvin, and then the Helmholtz free energy, which is the internal energy minus T times the entropy, is equivalent, then I know that the beta phase has higher entropy. And so the entropy of the beta phase is about 70 joules per mole per Kelvin larger than the alpha phase at low temperature. And so it's really because we're, so the reason we observe the beta phase at room temperature is because even though it's higher in energy, we're turning on the vibrational entropy because F equals U minus TS. And so there's larger entropy in the beta phase. And so we observe the beta phase at high temperature. But then as we go to lower and lower temperature, the magnitude that the entropy contributes to the free energy diminishes, and then we go back to the alpha phase. So if we look at these two phonon density of states, we can kind of imagine why the beta phase has higher vibrational entropy. So if we're kind of looking at these density of states as a function of frequency, we see that a pretty substantial fraction of alpha tin, so the low temperature phases, density of vibrational states, are at these very high frequencies above about 5 terahertz, whereas all of the beta tin vibrational frequencies are below 5 terahertz. So that means that if we're not accessing vibrational frequencies above 5 terahertz, then there are many more states for beta tin to many more vibrational states to occupy for beta tin than alpha tin, because 100% of the vibrational frequencies in beta tin are available below 5 terahertz, whereas only, let's say, 90% of alpha tins are available. And so that's what gives rise to this higher entropy for the beta phase. All right, so that's all I have for today's lecture. I guess I'm letting y'all out a little early. Feel free to ask any questions now, and I'll definitely stick around for a few minutes.